Okay, guys, let's get started. So let's see. So first, something about like the housekeeping and schedule. So I think what we're gonna do is, unfortunately, I'll have to end up recording this coming Thursday's lecture because I'm gonna be somewhere. I'll probably be okay, but I'm not 100% sure. So just to be safe, I'm gonna record the lecture and put it up. So today, what is it? September 29th. We're gonna cover sort of half-wave regulator, and then October 1st we're gonna do full wave. I guess this is rectifier. Sorry, full wave rectifiers. And then October let's see, 6th, I think it's Tuesday. This is Tuesday, Thursday, Tuesday. We're gonna like review the homework. And then Thursday, the October, no, wait a minute, this is, yeah, Tuesday, 7th, 8th, I guess October 8th, we're gonna have our second quiz. Okay, and then we're gonna start bipolar transistors. I also put this up on Blackboard. Okay. How's so we just got done with, like, I don't know where we are in the number of weeks of what we're doing with the remote learning. Anybody have any comments, suggestions to make things better? Any thoughts?
No, I think it's going pretty good.
Okay, well, feel free to shoot me an email if you guys, want, like, and have any suggestions, and we'll try to tweak it. From my point of view, I think things are going well, just because they're going better than the way they went last semester, when we kind of halfway through ended up doing things remotely. But I'm sure we can improve it. Okay, well, so that's the schedule, and let's get going again. So I think where we stopped last lecture, we were talking about particular application of diodes, and this is to basically build something that you can charge your DC device through. So sort of working your way. I think this is one of the circuits that all of you, as long as you're doing microelectronics of any kind, are going to see. You're going to see it sooner or later. I mean, if you just crack open your PC or whatever, you're going to see a situation where you're going from the wall, which is that 110 volts, 60 hertz, to something that then ends up giving probably, something like 3.3 volt DC to your device, to laptop or cell or something like that. So through something here, and coming out of here might be, I don't know, we said 4 volt RMS, 60 hertz. Okay. So we said, okay, so this guy is, the problem we're trying to solve is we have an AC signal. So this is a transformer. So on one side of the transformer, we have 110 volts. On the other side, we've dropped the voltage down to something more reasonable. I don't know, maybe again, 4 or 5 volts, something like that. And then the problem is, how do you get a DC out of this? So the problem is, this is all AC, no DC. Whereas what you'd really like is something like that for your device. So you want all DC, okay, to I don't know, whatever, laptop or cell phone. And again, I feel like all of you guys, we deal with this device. It's in a box, usually somewhere, but we see it all the time. So I think, and again, and once you get into building anything on a board, this business of regulation and getting the supply good ends up being a big part of your life. Although it just seems like the starting point, but a lot of times it turns into a big issue. So let's what we said last time was, if we put this signal, this input, so this is our input essentially. So here, so I'll call this V line. Let's call this V in. Okay, so if we take our V input, put it through a capacitor, so call that C1, put it through a diode and a capacitor, we said, oh, that was pretty smart, because what happens is, if I look at V out, let's say this has got a voltage drop VD on. We said when the input gets to VD on, so here the diode turns on and conducts, and then when the input has this sort of a negative going direction, this diode would have to pull current away from the capacitor, which it cannot do. So all the charge gets left on the capacitor. So this guy ends up being, let's call this V peak. This guy ends up being V peak minus VD on. And it's a DC value. Past this point, all the way out here, it's a DC value. And looks like we're done, right? It basically, that's kind of what we wanted, and we get this DC value here. And of course, life's not so simple, because in a real situation, what you have is, so let's say this was the circuit you designed, life's good. Here it's going to be a DC value, but there you're going to have a load. Let's say this is your cell phone or your laptop, and you can't discharge the capacitor going back into the diode, but you sure can discharge the capacitor through this laptop and cell phone, and this is what it's going to do, because it's pulling current. It needs current to do anything. So it's going to, in reality, it's going to discharge this capacitor, and what it's going to do is it will, as soon as the diode goes off, it's going to start pulling on this, discharging this capacitor until the diode goes back on, and we'll look at this behavior, okay, and what this means. So in reality, what you have is you have the capacitor, and then you'll have the load of your device. And to make things simple, you can't always do it this way, but to make things simple for now, we're just gonna pretend like it's on the average. On the average, it's a resistor. Okay, so it's a resistive device. So this is modeling your cell or laptop. Okay, so and again, in reality, what your, I don't know, like your laptop is going to do is, if you look at, so this looks like it's a constant current pull. All right, so this looks like a constant current pull from your device, but in reality, I don't know, any kind of device is going to have, if you look at the current versus time, it's going to go up and down. Let's say your cell phone is, is like sort of sleep here, or and then you turn it on and so it's just all it's doing here, it's checking periodically if it gets a phone call, if call comes in, say something like that. Then at some point you're going to turn on Spotify or something and play and stream data. And at some point you're going to make a phone call. And it's actually a lot more chaotic than this. And then you're going to, I don't know, do different things. So the way the current draw works from your load, we're saying on the average, it'll be some kind of a resistive value, just to make life easy for us to do this calculation. But in reality, it's much more complex than that. But okay, so let's see what happens if we do I'm going to do an example, and you guys can see the problem we have. This is example 3.25. And let's see, the question is, so we have a laptop that takes up 25 watts on the average. Okay, and it needs a 3.3 volt power supply. So what is current draw? Again, on average.
Oh, I see. So that's how you modeled it like a resistor, right?
Yeah, well, you're just saying it's like a resistor, just to make it easy for now.
Oh, okay. Thank you.
Yeah, sure. So so basically power, there's a lot of different ways to look at power. You can either look at it as I squared R, or sorry, I squared V. What is that? I squared R, or V squared over R, or you could do V times I. Okay. In this case, we have power and we have voltage. Right, we have power and we have voltage, and we want I. So basically what we say is the current is, we just write this down as power divided by voltage, or 25 watts over 3.3 volts. Okay, and this ends up being around 7.6 amps. Okay, which is, it's a lot of current. But so that's the current that your laptop will be drawing on average from that capacitor. And again, we'll see how that's like a lot of current, and it's going to give you a lot of headaches, that load. Okay, so if we model, like going back, if we're just saying, hey, this guy, again, this is the average current, right? So if we say we want to model this as a resistor, what we say is this resistor, the load, has a voltage and it's pulling a certain current from it. So it's got 3.3 volts and the current is 7.6 amps. So R sub L looks like it's around 0.44 ohms. Okay, so if I was gonna pretend like this is my laptop, this guy is gonna be 0.44 ohms. Okay, so this is this laptop simple model. Okay, and again, this is like a large current leading to a very scarily low resistor. That's going to discharge. You need a really big capacitor to keep this thing from discharging too much. Okay. So let's see what happens here. So we got.
Professor, can I just ask you a small question?
Sure, go ahead.
I know that you know a lot more. So you said that resistor load is a lot. Could you show us, like, put it into perspective a little bit, how much that really is? Because we're too used to like 1 kilo ohm, and we're like, oh, it's just 1 kilo ohm, but you're like, oh no, wait, that's a lot, of resistance.
It's a good question. Like if you think about your power supplies in the lab, I don't know if you guys have taken lab courses or not, but like that's like usually the output is like a 10 amp or something, like a big bench power supply. It's got a 10 amp maximum current. And basically that guy, like this laptop, is drawing enough current that big bench supply, that'll have to get used just for that laptop, just for the average current. Okay. So I think until you start dealing with things on and off, it's hard for me to say. And like big means different things to different people. Like if you're gonna go and work for Edison or something, their currents and voltages and stuff are gonna be much higher. But for microelectronics, again, I think like that is all I can say is a low value resistor, especially if you have this much voltage across that. So like 25 watts. See, I'm trying to figure out what would, like your cell phone would probably draw 1 or 2 watts while you're making a phone call. Okay. So imagine like making some days when you're like making a phone call and it takes a long time and sort of your phone gets a little hot. So I kind of get that feel for that. That's like only just 1 or 2 watts. Or, when you got your Mac, I don't know hopefully you guys have better laptops than this, but you put your Mac on your lap. I mean, this is at this 25, 30 watt level or whatever. After a while, it starts burning your lap. You got to it starts heating up. So that kind of thing, when you get that physically large of an object, hot enough that it's like noticeably hotter or uncomfortably hot, I guess that's a good testament to how much power it is. But it really depends on the stuff that you normally see in your life. Like lately I've been playing around with like these Goal Zero. It's a company that they sell like solar, like portable solar panels and portable batteries, etc. And like I my laptop, if I have a battery this big, this thick, that can give my laptop one one full charge. So it's a lot of, like, to me, like these are like, it's a, when you think about like physically in your daily life, how many things are like annoyingly that large. I don't know how to look, like a laptop is a pretty physically big thing. If everything was this big and it pulled that much wattage, I don't know, like you just have a pretty hot room, I guess. I don't know. It's just like, yeah, I think that's another test is I don't know if you guys been in a lab or in your home, and you've got a bunch of laptops or something, or a bunch of desktops running, things get hot. To me, that's kind of like, I don't know, that's probably not a good answer for you, but I think you just kind of get used to currents and voltages and power values and what's a lot and what's not.
Is that
Um,
why I have computer rooms that are really cold, keep them really air conditioned?
yeah, that's, otherwise, you're going to get a meltdown. And in fact, it was funny when, like you're making the point, for a while when they were doing the Bitcoin mining. I don't know if you guys remember that. That was like really big a couple of years ago. Maybe still is, but people were actually investing in putting those like server rooms up as far north as it would go, so they'd be like in a cold climate, because just the cooling of those server rooms was expensive, and they were trying to drive their price down. So they would go up to like Greenland or Newfoundland or whatever, to put these places up in those kind of places. So so anyway, you get kind of used to different things for a while. I'm trying to think what, like if you have, yeah, like imagine if you had, do you guys have like these Ring doorbells? I don't know if anybody's got those, but you charge them up. You guys are students, you aren't worried about being robbed, I guess. But you're, anyway, it just I think the battery size is a good indication. Once you get to like large batteries, you go, man, that's sucking up a lot of power. So sorry, just got to get used to it. I hope that gives you an idea, but it is dependent on like what if you're working, for another example is if you're working for Tesla, you're talking about massive currents that you're drawing. Like I'm getting, electricians are coming tomorrow. They're going to spend all day to put in my Tesla charger at home, and it's because just it's got this huge battery the size of a, I don't know how big is the size of a mattress or something like that.
That's actually what I do for work.
Oh yeah.
I'm an electrician. I put in Tesla chargers over in the near the coast.
Oh,
Oh,
nice.
Yeah,
nice.
over
Yeah.
in the Santa Monica area in Venice.
Ah, nice. I should have called you, William. Sorry.
Uh,
Thank you, Professor. Appreciate that.
Okay, sure. Okay, so let's say we have this thing. So now let's look at the case. Oh, again, what happens when we got this kind of situation? Not the exact value, but let's just call it. Alrighty. So we have our C sub 1, R sub load. Okay. So again, what happens is we have time, we have voltage, So, by the way, guys, just to again, in terms of the the three ways of looking at graphs for this class, probably for work too. Notice we have, I think I'd mentioned this before, but like in the tests, you know, it might get confused. We have sort of three graphs. We have VD versus I sub D, so voltage versus current, and usually this is in the device, in the diode or transistor or whatever. Then we have voltage in versus voltage out. Okay, this is when you're looking at your device in a circuit that's generating a voltage. So this is type 1, type 2, and this is sort of a type 3, which is voltage versus time. And we're going to pretty much talk about that type of graph, that kind of input versus output characteristics in this lecture. But anyway, so the V in is this. So let's call this thing the peak voltage. Okay, and then we said that what happens is when V in gets to VD on, the diode turns on. So now I'm going to draw V out. The diode turns on. And again, normally or not normally, if we only had the capacitor, you couldn't discharge the capacitor, so this would kind of stay high. But indeed what happens is at this point, let's call this T1. So at T1, so let's call this D. D turns off. And the reason it's turning off is because this point is going lower than this point, and there's no way for the diode to pull current. But what happens is your load resistor starts pulling current, so you start getting this drop. Okay, but at some point here, I'm not doing a good job of drawing this. Oops. Ah. Okay, at some point, this guy is going to droop enough during when the input's high going that is going to sort of recharge up this capacitor. So this will be the point where, so at T3, V out has gone down to V in minus VD on. Okay, so notice V in is moving, right? So two things are happening. V out has drooped, and V in has gone up enough that now that difference is VD on. The diode turns back on. As soon as the diode turns on, V out starts following V in again. Okay, and then when you hit this peak, the diode turns off again, and then this whole cycle repeats. So if you look at, let's see, this region here. So just here. This looks like the diode is on. And we have it, our C1 and our load. Sorry, I should have drawn the. So the diode is on, but it's got a VD on battery. So we get that drop across it. And then let's take another color. This from here to here, the diode is off. So it looks like an open switch. Got the battery, but it doesn't matter. It's just floating. So C1 and R sub L. Okay, so for the whole time that you're, in this light blue, you're just discharging because the diode is off. And then here, let's go back to green. Here, for this very short period, again, the diode goes on and charges up the capacitor. It charges up the capacitor and then it goes off again. So again, the cycle repeats. And then here again, the diode is open. So what happens is for a very brief, once you get past, once you get started, every cycle for a brief period of time, the diode sort of wakes up because the conditions are there for it to turn back on. It, dumps a bunch of current into the capacitor. So here the diode is dumping a bunch of current into the capacitor to charge up the capacitor. It also has to put, because you have the load in parallel with the capacitors, momentarily you're also providing current to the load. But it's not typically most of your current is going to charge up the capacitor. We'll see that. Okay, so and then this thing, this thing, the difference between this guy's high and low, this difference, this delta V called VR is called the ripple. Okay, so ripple is bad. It's something you don't want. You'd want a completely flat, smooth line there supplying the voltage to your circuit, but you're getting this ripple because of you're discharging the capacitor you dump the charge on. And so you want to reduce that ripple as much as possible. So the goal is reduce ripple as much as possible. Okay. So, and then because the bigger the cap is, the lower the ripple. So, well, let me take a step back here. So typically when you're designing the circuit, you don't have a control over this load current. You bought that device or something like that, right? And you don't have a control over the wall, 60 hertz input either. What you do have control over is really just this thing. To first order, of course, is the size of this capacitor. Okay, that's pretty much what you can pick for your circuit. Again, because like somebody else designed this thing and you're trying to use it. So anyway, this capacitor is typically called a smoothing or filter capacitor. Okay, so there's several like long-lasting enmities in the engineering business. Okay, there's the biggest one is probably the enmity between mechanical engineers and electrical engineers. But the other enmity is between the people who design the stuff in this load and the people who design the rest of this stuff. Okay, they just are always at each other's throats. So, for example, let's talk about this. So, at my work, the kind of stuff we do, where the guys are designing the chips. Okay. So these chips are basically this load approximately. And what we try to do is we like to use as much current as possible. I mean, within some other limits of, that's why it's supposed to have mechanical engineers, because they have to build the enclosure to remove all this heat and all that stuff. And they don't like us either. But certainly within those limits, we want to just throw current at this chip until somebody stops us. Okay, just because it makes your life easy. You want to throw in as much functionality as you can in there, even more than what the customer spec. That's just the nature of design engineers. And it just turns out that sort of the lazy thing to do is to use up a lot of current to do whatever you're going to do. Okay, so one is you want to have a lot of current. So this is us. Okay, and two, you want to tell whoever's using your chip is don't give me a lot of ripple. You want to say very low ripple. Because ripple makes our life hard. It sort of eats into our noise margins. We like a nice smooth input voltage. So we design this chip, and then we write the specs, and the specs invariably have like a very high current, like as high as we can get away with. And we're telling the person that who's going to use this chip, make the ripple as low as possible. Okay, so on the other side, so this is the enemy, or the guys that are gonna be using this chip. They have to build this circuit, okay, to use the chip, the power supply, and they, having what they want to say is, look, you can have a high current or a low ripple, but not both, because as you can imagine, the higher the current, the more the ripple, and vice versa. So we're making their lives difficult. And this is a constant negotiation for people who are designing the chips versus using the chip. Okay. And so, because what happens is here, sounds like, well, we just said, as somebody who's designing this circuit, is designing the circuit to use the chip with, is we have control over this capacitor. So it just sounds like, well, all you have to do is to buy a big capacitor and put it on your board. But the problem is, as we'll see in the examples, for example, on the laptop, etc., big capacitors are so large. Let's say take large value capacitors.
Professor, does that affect the power factor?
The what, sorry?
Does the large capacitance affect the power factor? That's where you're going right now?
What do you mean by the power factor?
The power factor that when it's how is it called? When you have the real power and the imaginary power, and the imaginary is reactant.
Oh, I see what you're saying. No, we haven't even gotten into that imaginary real and reactive power, et cetera, yet. But I
Okay.
like a big. I think what you're saying is, correct me if I'm wrong, but like big capacitor also have a big sort of inductance built in. Is that sort of where you're going in? It sort of it has
Yeah,
the
yeah.
sort of reactive. Yeah, that's a whole other problem. So I'm probably not going to get into that just because it'll make things complicated. But yeah, it'll basically a big capacitor tends to want to ring as well at low frequencies, which is bad. But I'm not. That's a good point. But I wasn't going to mention that here because that's a whole other. But maybe we should. So one is large value capacitors is physically large. And two, they are expensive. So the question is, what do any of these things mean? Like large, expensive, um, like the bill of materials is like a very, very important thing. And what happens is a bunch of little things add up. And so expensive means different things to different people, but you got to think. Um, let's say you're buying, let's say, an inexpensive laptop. I don't know how much is an expensive laptop these days. Um,
500,
how much?
500 around there, 500.
Okay, so 500. So for a $500 thing that you buy at the store, the maker, to have a decent business, has to make that thing for $250 or less. Okay, ideally you want to be at like $125 or less. Like Apple, Apple is like a very, very good company, very profitable. So if you have, if they sell you a $1,200 iPhone, their cost is around $300. So they've got a very profitable business. A laptop maker may not be that profitable, but let's say if they're selling it to you for 500, they got to make it for 250, including the display, including all the labor of putting it together, including all the shipping, and including all the components. Okay. So if you have like a bunch of, and then you put in the processor in there, I don't know how much a processor is, probably like 100 $125, $150. I don't know, like an Intel processor, right? So you're putting all these other components as things, a few dollar, $5, $10 piece of something is very, very expensive. Okay, so they don't like it. And then in terms of things being physically large, again, if you look at a printed circuit board, like a motherboard on in your computer, if you've ever looked at it, or maybe look at it on YouTube or on the web, you can just look around there and see where the big hunking pieces are on the printed circuit board, and those are going to be these guys. Just you physically can see them. They're just these huge sugar cube looking devices where everything else looks like a grain of rice or something like that. So those are important. And then I think it was Aaron that mentioned this, but you have sort of a huge inductance and you have a large capacitance too. So these are all like really bad things, and you don't want to do that. So there's always this fight between this thing and these guys. So you can't just throw in it a huge capacitor. You want to put in as small a capacitor as you can get away with. And here's the way the different things can look, right? So if you have, again, redrawing this guy. That's my time V. So this is my VN. Okay, so let's say I had, this is what whoops, I'm drawing this badly. But so let's call this like what would happen if you had a large capacitor. You have a droop. Okay, but it's not too bad. And let's say I have a, well, I don't say it's too bad. Let's just say I have a smaller capacitor. Okay, so then if I had a smaller capacitor, because it still gets charged up, because here the diode is on, but when the diode turns off, assuming R sub L stays the same, it's gonna start discharging faster. It'll still go up to the same value and then again start discharging faster. So it's gonna have, if this is VR for large cap, this green VR is going to be for a smaller cap. Okay, and then let's say you really screw up your design and make the cap way too small. What happens is it'll like immediately start discharging, and you don't even get, there's not even a meaningful ripple because you'll just completely discharge between the cycles. So this is the too small. Okay. So basically by picking different capacitor values, you end up with different ripple sizes. Okay, so let's try to figure out what to relate the value of the ripple voltage, because that's the spec you'll get. You'll get, somebody will tell you design me something, or you want to design something with, I don't know, like 100 millivolt ripple, because these guys told you I want 100 millivolt ripple, so I want this. So now you got to design that, right? So now you got to figure out what's my capacitor size for it. So here's how you figure it out. So when you look at it, in the case where the diode is turned off, so this is C1. So let's say you're right at this point, right? The diode has turned off, and you have a voltage of VP minus VD on here. Diode is turned off, and I got a battery here, and this battery is VD on. Okay, so now it looks like I have basically an RC from a time standpoint with, initial condition of VP minus VD on, and then this RC network is gonna discharge this point. And I'm not gonna drive this, but hopefully you guys have seen this before, but it's this exponential drop of this RC network. So it's the V initial times the exponential of minus T over RC. So it looks like VP minus VD on e to the minus T over R sub L C sub 1. So this is the equation for these curves coming down as a function of time. So at any point along this curve, once the diode turns on, so between these two times, this is the situation you have, and this is the equation you have. Okay. So, okay. So it's got an exponential drop. The smaller R is, the bigger C is, the less of a drop you have. So what we want to know is, how big, what size should we make C given a certain R sub L. So I'm going to pull in. So this is, so we said this was, say I call this T1. And when the diode turns back on is T3. Okay, so but this is true for T being T1 to T3. Okay, T2 is given when this guy. There's different T2, so let's just call this T3. Is when it turns on. Everybody with me so far? Anybody not with me? So basically,
can I just see the graph with T1 again?
Sorry.
Sorry about that. Can I see the graph with T1? Oh yeah, there we go. Thank you.
Sure. So basically, the at some point the diode turns off, the resistor is pulling current from the capacitor, and it starts discharging the capacitor voltage with this equation as a function of time. Okay.
At the denominator above that E, that's RL and C1, right?
That's correct. Yeah.
Okay. Sorry. Thank you.
Yeah. Sure. Okay. So we want to, again, this is an exponential thing. You guys know how much we dislike exponential type equations in this class. So as soon as we see an exponential, we try to get some simplification to get rid of exponential, and this is no different. So let's see, we're gonna, and as usual, we've got that Taylor series expansion. If you guys remember, we used this for the small signal approximation, and we're going to use it again here. And the idea is if you have something like e to the minus like something, okay, let me just rewrite that. Looks like a t, e to the minus I don't know, epsilon or something. Okay, this is equal to 1 minus epsilon squared over 2, da 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 da. So if epsilon is much smaller than 1, then we can just, this exponential of minus epsilon is 1 minus epsilon. So this is kind of the same trick we used, if you guys remember, for a small signal approximation to get our exponential curve of our diode look like a line. I mean, sort of the same technique we're using. So really, this droop is an exponential type droop, so it kind of looks like what I drew here. But because we're saying if the case is minus t over r sub L over C1, if this is small enough, if TRL over C1, if it's small enough, then it looks like a line, basically. That's what we're saying. If it's small enough, it looks like a straight line, whereas it's just sort of it's really an exponential, but it'll look like a straight line if it's small enough. And you can make it small by making C large or making R large. Again, R you don't have control over, but anyway, so you can make it small by making C large. Okay, so anyway, what you end up with then is if I use this approximation with these numbers, so we end up with V out is VP minus VD on 1 minus T over RL C1. Okay, but approximately. This is a function of time. Come on. So everybody's with me so far. So what we did was we used basically this Taylor series expansion approach, which is sort of this approximation to get a linear approximation of what our droop looks like, our voltage output looks like once the diode is off. Okay, let me rewrite this as V out T is VP minus VD on minus okay. So if I just rearranged it. So rearrange to end up with these two components. So this is sort of the initial voltage we're left with. So this is the starting point. So this is the peak value. And so, or V out at T equal to T1. Okay, that's what we know. We started off at that. And this is the droop, or like the falling ramp. As a function of time. Okay, or VR or ripple, however you guys want to look at it. So this is at any point, this is how much you've fallen from your peak value. And so this is really the ripple we're looking at. Okay, that component. And that's what we want to control. Okay. And then, separately, anyway, so typically, I mean, I don't know if I want to make this categorical, but typically you don't have control over these, right? You have a load, you've got a bought device that has a certain current pull, and you've got a certain input. So basically you can play with these two things. Well, you can't really play with time even that much, but basically you can play with the capacitor. So this is the stuff you can kind of control. Okay, so then let's see in a typical case what happens. So this is the droop at any one point. And the maximum droop, so sorry, let me do this. I said this wrong. So this is not the ripple, because this is still at any, if I go at any point, this will be a different value. These are the different points you're in this line here. Okay, as you're going down. This point, the maximum point is the V sub R, or the ripple value. So let's see how we define that. So if you look at the time, right? We have so we have this. If you look, so let's just define one thing first. Is you have this period from this peak to this peak. Okay. And that is, let's call that the, this is the period, which is 1 over the frequency of this. So if you had a 60 hertz, so for input is 60 hertz, which is what the wall is, wall voltage. Okay, the period of that is going to be 1 over 60 hertz, or 16.66 blah 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 6, or just call it 16.67 milliseconds. Okay, so if we have the wall, so if you have a 60 hertz signal coming in, this whole period is 16.67 milliseconds. So if we say, so what is the maximum value of t, right? We basically, we're discharging from here all the way to here. So from T1 to T3, we're discharging. We're on for just a very small period of time before we start discharging again, right? So we basically can say that the maximum droop value happens when T is approximately Tn. Okay, because this period is so, the full Tn includes this small period when the diode is on, but for the sake of simplification, we're saying like for almost the whole time, this thing is drooping. Okay, it's just because it turns on momentarily. Okay, so if we plug this in to here, okay, and we just look at this component. So if we plug this in, if T is equal to Tn, and we just look at Vp minus Vd on over RL T over C1, that's equal to VR or ripple. Did you guys follow me there? So to find the maximum place where you droop the most, you go sort of a full period of your input away, which is this distance. Okay, and you see just how much, just the droop part of it. So basically this VR then ends up being Vp minus Vd on over R sub L C sub 1 F n. Sorry, I jumped a step here. Just because Tn is 1 over Fn. Okay, so that's the main equation here for if you did not screw up your design, then this is the equation. If you want a certain V sub R, a certain droop, say 100 millivolts or something, then you can pick these numbers, some of them. Basically, you can pick C1 because Fn is what's coming from the wall. That's a known. R sub L is something that the device designer has already done. So you can basically pick the capacitor. Okay. So let's do a example. Are we doing on time? Crap. So here, example 3.27, it says, the transformer took the 110 volt wall signal at 60 hertz to a 9 volt peak. Oh, what happened to my writing? Sorry, guys. So transformer took 110 volt 60 hertz signal to a 9 volt peak to peak 60 hertz signal. If we want the ripple voltage to be 0.1 volt, select C1. then assume VD on is 0.8 volts. Okay. So basically, what we have is after the transformer, we end up with this voltage versus time. So this is after the transformer kicked off. We get a peak-to-peak voltage of 9 volts, which is this guy. So that means the V sub P, basically for our equation, is 4.5 volts. And then means that the diode turns on when the input is at 0.8 volts, which is our VD on. Okay, so it kicks off there. It goes up to 4.5 volts minus 0.8 volts. So that's V sub P minus VD on. And then it starts to droop. And then it's going to repeat itself. So the question is, we want this thing to be 0.1 volt. So we have to pick the cap. Oh, and then by the way, this is for the laptop in the previous example, which I think was in 3.25. So if you remember that one, the effective R sub load was what was it? 0.44 ohms. Okay. So all this says, so I'm going to use this equation for the ripple, okay, is Vp minus Vd on over R sub L, C sub 1, and F in. Okay, so Vp minus V on, we said, is 4.5 volts minus 0.8 over R sub load was 0.44 ohms times C1 times 60 hertz. Okay, and we want 0.1 volt equal to this. So we can arrange stuff around and we end up with a C1 of 1.4 farads. Okay. And so, I don't know, again, this is like a very large capacitor. How do I define that? It'll be a farad capacitor is like very big. I'll see if I can find some examples for the lecture, but this is a very big capacitor. Okay, so at this point, you know, maybe this is the time to go back and talk to the designer of that circuit that you're driving, of the laptop, and or maybe we should have done that to begin with in the design cycle and say, look, you know, 0.1 volt ripple is just going to make this thing too expensive. You got to design your chip so that it can live with a half volt ripple, or otherwise just going to end up with this gigantic capacitor that maybe I can't physically fit into my tiny laptop, or, you know, it's just too expensive for my budget. You got to do a better job of designing this chip so it can handle the bigger ripple. Okay. So let me finish up by quickly walking through. Everybody get that? So basically the problem is, you know, when you look at the homework problems for these half-wave rectifiers, you're always got one of these factors, and you have either you're looking for a particular ripple, and you got to decide the capacitor value, or you have a maximum capacitor value, and you know you got to figure out what kind of ripple you have. But basically, you go back to these equations. So when all is said and done for the regulator or half-wave rectifier, you kind of like, I really feel like this equation is sort of like the be-all and end-all of this thing. So don't go, if you have a half-wave rectifier, look at this first when you're going to solve a problem in a quiz or homework. This is like the important equation, and usually ends up being, I feel like these are like the simpler problems, although it's sort of a complicated circuit because things are discharging, etc. But the solutions are typically fairly easy. Okay, so let me just talk about one more real life thing with this circuit. Is that, and this isn't gonna come on the test or anything, it's just something for you guys to remember, because at some point in your life you're going to pick the wrong diode and it's going to blow up, and you're going to remember I told you guys this. So when we have this thing, let's say we have this gigantic capacitor, right? You have a C1 of 1.4 farads or something, and then you have your R sub L, which is 0.44 ohms, 0.44 ohms. And this guy, only, if you remember, I said when you have, this is your input, this guy at, let's say it's come down before like this, and then you're gonna go, this is just badly drawn like this. So you have only this tiny amount of time to supply current. Time. So that, again, the diode is off from here to here. So most of your cycle diode is off. Only for a very tiny amount of time is it on. And basically, it's got to supply all of this current to charge up IC1. And you still have to supply the current to I sub RL while you're on anyway, because these two currents are in parallel. So this I total can be very large. Okay, so, and it's easier to define what very large means in this case, is because, you know, if you get a diode, you get a small diode. Always, when you especially when you have, when you have diodes, resistors, transistors, regulators, always look at the max power consumption that they can take. Either it's the package or the size of the semiconductor physically, but this maximum current can be very large just because you have a very small amount of time that you have to load it up. So the current to charge up the IC1 is just a C1 dV out dt. So that's C dV dt, right? And so it's kind of maximum right here when you turn on. This is the biggest dV dt. So that ends up being the point of maximum current. And I sub R, when you're on, stays the same as just Vp minus Vd on over R. So that's more of a constant thing. So I'm just going to give you guys the equation from the book. And again, this won't be in a test or anything. It's just a warning to everybody to worry about the size of their diodes in circuits like this. The input frequency 2VR over Vp. This is in the book. Okay, but so if I just example 3.28. So for that circuit, so we had a C of 1.4 farads, we had an R sub L of 0.44, we had a peak voltage of 4.5 volts, and we had F in of 60 hertz. So W is 2 pi Fn. And we wanted a ripple of 0.1 volts. So if I plug all this stuff into this guy, you end up with a peak current of 517 amps. So that's a big pattern again. So it's like, this is a real bad design. This design's going someplace really bad. Again, if you think about next time you're in the lab, look at those bench supplies and how much current they can supply. It'll be nowhere close to 517 amps. Okay, so that means it's going to collapse that bench supply, which is like this big monster that you have sitting in the lab. So basically at this point, you see this is really not a good idea when you have something that's pulling a lot of power, or 25 watts was this, which how much current you had, to live with a ripple of 0.1 volt on that thing is a real difficult problem, because you have a huge peak current that's going to blow up your diode, most diodes, or you have to get an extremely large, expensive diode, and you have a big capacitor, et cetera. So it's not a good design. So again, just remember that, and you also remember that, so this is the max or the peak current that you have to worry about. And also remember that this kind of circuit, the input, from the input to the peak value was also, in this point, the diode had to have 2 times, sort of approximately 2 times the peak value. So you need to worry about peak current and worry about the breakdown voltage of the diode. So diode, these are in the diode specifications, so you have to make sure you pick the right diode. Okay, guys, that's what I had for tonight. Any questions?
Not really, Professor. Those
Okay.
examples explain a lot.
Okay, thanks, guys. So anyway, so don't forget, Thursday, it's not going to be a live presentation. I'm going to record it and put it up. And then anyway, so I'll put in the schedule for the quiz 2 on the Blackboard. Okay, guys.
Also,
Yeah.
Professor, just to make sure I understood, we're not having a meeting session, right? Like at the time we're scheduled, 5:30. You're gonna upload a video, correct?
Yeah. Yep. And you can just watch it whenever.
Okay.
Okay, guys. Thanks.
Thank you, Professor.
Thank you, Professor.
Thank you, Professor.
Thank you.
Thank you.
Bye.
Hey, Professor.
Take care.